This set of videos will cover alternative methods for getting composite data into HyperMesh. In the introductory tutorial with the HAP model, we covered manual creation of all the necessary ply-based composite data. So we started with some mesh geometry. We created the template property, set orientations, and then we manually created our ply shapes, materials, plies, and laminate. Sometimes this is necessary, obviously, if the data hasn't been defined anywhere else, but if it has, it can be imported directly into HyperMesh and automatically generate the composite data, so the shapes, materials, plies, and laminates. 3 core types are supported, just a basic spreadsheet format, and then CATIA CPD, and FiberSim. So the general process for importing this data is we still start either with some meshed geometry, which was pre-existing in a HM database, or solid or shell geometry can be imported from something like CATIA. We'll still define our template property and our orientation, so our stacking direction and our material reference orientation, just the same as we did previously. And then we'll come into this automated import alternative method for generating data. Once we're at the import step, this is what the process looks like. For CAD-based data, so CPD or FiberSim, we're going to import that data into HyperMesh with a file import geometry. Once it's brought in, usually what we'll do is use an imported local system to assign as our material reference orientation. Then we'll do what's called a realization of ply geometry onto elements. And what this realization is doing is converting ply shape data defined as geometry. Depending on the file type, it's defined with different methods, into shape data defined by a selection of finite elements or an element set. Following slide has a little bit more detail on what exactly is going on with this, but in general, the bounding lines of the ply shape are somehow defined in CAD, and when we do this ply realization, those lines are being projected along the element normal onto a specified set, usually a component of elements, to determine the shapes as defined by element sets. There are a few different CAD types supported for ply realization. CATIA uses bounding lines. It also uses solids to define core ply types. FiberSim uses an alternative tabular or meshed geometry type. And do note that it isn't required that this type of data is imported to define ply shapes using CAD. Any of these methods, lines, surfaces, or solids, can be manually specified on one or more plies if it's more convenient than selecting element sets, and then realized to generate final element sets. So after the ply realization, we'll arrive at a fully defined HyperMesh ply-based model. Exactly the same data as we previously manually defined in the introductory video. And once we're at this point, we can export data back to CAD again. And the supported formats are listed here. We can do CATIA composite links, FiberSim H5s again, and we can go back to spreadsheet. For the spreadsheet process, it's a little bit different because we don't actually have the ply shape geometry. So usually the starting point for the spreadsheet process is that we'll go all the way through the process we reviewed in the introductory videos until we get to the ply shape step. We'll create our ply shapes, and then upon import of the spreadsheet, this will populate or create our plies and the laminate that they're stacked in. This video covers the steps for a CATIA import and model build, as well as export back to a CATIA format. I'll begin with a file import geometry, and I'll navigate to the CAD.io data section. On import, we're going to grab this cap part and open. And when I'm importing CATIA data, it is important to come down to the entity selection and import options and make sure that the composite option is checked. If it's not checked, any composite data in the cap part will not be imported. It's checked, so I'll go ahead and import. This is going to bring in a similar model to what we built in the introductory series. So I have a component with some geometry. In this case, it's just shell geometry. You may or may not need to mid-surface solid geometry first, or if you're starting with previously meshed and mid-surface geometry, you can skip any meshing steps and go straight into the composite specifics. I also get a couple materials, it looks like, a local system. This is usually what defines the material reference orientation in CATIA, and I get some plies and laminates. If I open the composite browser from the model ribbon, we'll see that I do have this one laminate, and it already has a list of stacked plies. In this stack, you'll notice that the shape, rather than being the name of an element set, is just a list of lines. And this is because CATIA defines ply shape geometry using bounding lines. So when we get into the ply realization, that is going to convert this data into element sets for us. We'll begin with the model build here. I'm going to go back to the model browser, and we'll start with a mesh. I'll use a general 2D mesh. I'll go ahead and select the surfaces that just got imported. We'll use 2.5 millimeters. We're still in millimeter Newton seconds, and I will mesh. Go ahead and just hide that geometry as well. Back in the composite browser, we're going to follow exactly the same steps we did for the manual model build to define orientations and template properties. I'll start with my template property with a right-click Create Property. We'll give it a name. And while I'm in here, I will set my Z0 or offset. Like the introductory example, we're treating this mesh as the tooling geometry. And finally, I will assign this property to the component which contains my elements. Next, I'll set my orientations, beginning with my stack direction, or my element normals. And this, again, is all exactly the same as previously. So on apply, maybe those are a little bit big, so I'll drop that down to something like 5 should work. That looks like they're all already going in the intended direction. So I'll go ahead and close out. Next thing I'll do is my material reference orientation. I'll select my elements again. And usually the incoming CAD data has a local system, or in the case of CATIA, Rosette, which defines this reference. So I'll use the system method and select that system. Note for CATIA import, I do want to verify if it's only a single system, whether it's selected under Ply System. If it's a single system, usually it's easier just to clear it out on the Ply System. But if you see hash marks here, that indicates there are multiple systems assigned to different plies, and you can just leave that data as is. The end result, if you left it, you'll still get a valid model. it'll end up just generating tables at the end as well. So generally, I prefer to do my material reference systems like we just did with an assignment onto the elements or property, depending on solver. Moving on, we'll convert this geometry-based shape data into element sets using the ply realization. I can do this by shift selecting all my plies, right-click, and realize. I'm going to select one or more components or a list of elements to use as my target. Usually this should be the component or components which contain your as trimmed geometry. I'll leave the default option here, which is a CPD normal projection. And almost never do I have to touch any of these additional options. So we'll go ahead and realize these. We can see upon realization, I get element sets defined, and the sets are assigned to my plies. So just as before, I can arrow through these and see those shapes just to verify visually that they look reasonable, which they do. And at this point, this model is fully defined. It's exactly like the final result of our introductory video series. And so all the same, for example, visualization options are available. I can look at my stack here with the 2D detailed thickness. We just looked at ply shapes. All the orientations will show. So for our purposes, this model is exactly the same as the end result of the introductory video series. With the model defined, if I made any changes, for example, and I wanted to get that data out of HyperMesh and back to CAD, I can do that now with a file export. And in the case of CATIA, I'm going to use this CATIA Composites link, which is the supported option. We don't have the ability to write CAT parts back out of HyperMesh. This video covers FiberSim import, model build, and export. Starting point for a FiberSim model build is meshed surface geometry. So we'll go ahead and bring that in with a file open HyperMesh model, and I'll select hat geometry. This is the same database we used for the introductory video, with the exception that there's no material data in this model. We'll bring that in with the FiberSim import. Next, I'll import the FiberSim data with a file import geometry. And I'll select the hat FiberSim H5. No other additional options are needed. I can simply import. And that brings in this file, any laminates. I get one laminate with a list of plies which are stacked. You'll notice there's no currently displayed shape here. That's because all the shape data is contained in mesh geometry in a specific FiberSim file. It's held in this table right here. So this table contains the ply shape information. It also contains any thickness changes or orientation changes of the fibers due to draping. I also get a couple materials here on import, as well as a rosette or local system which specifies my material reference orientation. I'll begin with the standard model build process by creating a template property. I'll give it a name. And while I'm in here, I'll set my Z0 equal to 0, such that this mesh represents the tooling geometry. And I'll finish by assigning this property to the component which contains my elements. Next, I'll set my stacking direction, or element normals. And again, this is all exactly the same as the introductory tutorial. Grab my elements. They'll just display the current stacking direction. Like that's opposite of what I actually want, so I'll use a reverse and apply again. For my material reference orientation, I'll use the local system which was imported with the FiberSim data, and I can assign that with a right-click Orient, Material Reference. Select all my elements. For the X direction method, I'll use System, and I will select the imported local system. Next, I will convert the FiberSim tabular data format of the ply shapes and additional drape data into our standard element sets. And I can do that with a shift select of all the plies in the laminate. I'll go ahead and right-click Realize the plies. I'll specify my realization region, either with elements or a component. So these will be my target elements that I'm attempting to realize to. And in the case of FiberSim data, I need for a projection option to use the FiberSim drape method. Very rarely do I need to touch the rest of this information. Usually the defaults work pretty well. And after realization, I'll get all the shape data converted to element sets. I can arrow through a few of these just to verify that they are reasonable. Looks like they are. And at this point, this is a fully defined ply-based model with all the same properties and capability as from the introductory tutorial. So I can do any visualizations. I can look at my through thickness, for example, to verify that this is all correct. See that ply drop there. This all looks good. And once I have a fully defined ply-based model, I can export data back to FiberSim. For example, if I had to make a design change, add plies, remove plies, change their shape. And I can do that with a file export. I'll use geometry. And I'll select the FiberSim H5 option. And with that, that completes import, model build, and export of FiberSim data. This video covers spreadsheet import, model build, and spreadsheet export. The process for a spreadsheet model build is a little bit different than the CAD process we covered previously, because the spreadsheet only contains ply data and the stacking sequence of the plies. There's no geometry data in the spreadsheet, and therefore no ply shape data. All of that must be defined in HyperMesh and then linked to the spreadsheet through ID assignments. This is the format of the spreadsheet. We have a ply name column. Every ply name must be a unique string. Similarly, a ply ID with a unique ID. Card image can be left as ply. Material name is a string. Any material in the HyperMesh database which has a matching string will take the appropriate assignment. We've applied thickness and orientation. Output results can be left to default, as can tmanu and drape ID. And also important for our purposes is the ESID. This is the ID of the ply shape or element set that should be assigned to a given ply in this spreadsheet. In HyperMesh, we'll go ahead and open the starting point model, which is this hat spreadsheet. And we'll follow the same process initially as we did in the introductory training. So we'll start by creating a template property. I'll go ahead and set my z0 equal to 0, as these elements represent the tooling geometry. And I'll assign my property to the component which contains the elements. Next, I'll set my orientations, beginning with my stack direction. Same process as we did in the introductory training. Go ahead and select my elements, display the current orientation. That looks correct. I want to be stacking in from my tooling geometry. Next, I'll do my material reference orientation. Again, by selecting elements and the appropriate method. In this case, I'll use a local system with the system which already exists in this model. I'll go ahead and apply to set my material reference orientation. And that gets us to the spreadsheet import step. To import a spreadsheet, I'll right-click Create a Laminate. And before I import it, you'll notice that I do already have shapes in this database as well as materials, which all correspond to the data defined in the spreadsheet. To import, I'll right-click the laminate, import spreadsheet, navigate to the Excel file. CSV is also acceptable, and I'll go ahead and open that. Upon import, we'll see any plies defined in the spreadsheet are created and take on any assignments for material and shape if they exist in the model. At this point, this composite data is fully defined. All the same visualization functionality exists now as in the introductory tutorial. I can, for example, turn on my through thickness visualization to spot check, verify that everything was imported correctly. And now on export, if I'd made any changes to this laminate, added, removed plies, changed a stacking sequence, I can export that data back to a spreadsheet with a right click on the laminate, export spreadsheet. And that'll write that data back out to Excel. And with that, that concludes the spreadsheet import, model build, and export.